In this program, we're going to take a look at an ingenious algorithm to determine the greatest common divisor of two numbers. So this is Euclid's algorithm for greatest common divisor. And I absolutely love algorithms that when you look at them, they don't look like they could accomplish much, but they do something just really well with very little code, very efficiently. So if we wanted to find the greatest common divisor between 12 and 8, the standard method is usually to list out all of the divisors. So you can divide 12 by 12, 6, 4, 3, 2, and 1. You can divide 8 by 8, 4, 2, and 1. And then what you do is you start at the end and find out, okay, well, 4 is the largest number that divides both of them. So 4 is the greatest common divisor. So now Euclid has an algorithm to find this without having to list everything out. So a good algorithm doesn't have to do the brute force method of checking every possibility. It has a more efficient way of solving it. So here's what it does. What you're going to do is you're going to divide the larger number, n1, so this would be 12 in this case, by the smaller number, n2, which is 8. And then you need to record the remainder of that. Then what you do is you discard the n1 and replace it by n2. So you shuffle up the value. So n1 would become 8. And then the smaller number, n2, would become the remainder. So n1 becomes n2, n2 becomes the remainder. And you just keep doing this until n2 becomes 0. Because eventually you're going to get to a point where the larger number n1 divided by the smaller number n2 is going to give you a remainder of 0. Even if n2 has to get down to 1 in order to do that, like if you're working with a prime number, or whatever, numbers that don't share divisors, it'll always happen eventually. And then whatever number is left in n1 is the greatest common divisor. So let's take a look at an example here. So you should probably record this as part of your program. It's a good example here. So imagine we had n1 is 345 and n2 is 150. So what our program tells us to do first is make a division. 345 divided by 150 equals 2, which we don't care about, with a remainder of 45. Okay, now what we have to do is we have to kind of shuffle up all of these numbers. So n1 is going to be 150. And then n2 is going to be 45. So n1 became n2, n2 became the remainder. And then we just repeat this. So the next time we do this, it's 150 divided by 45, which is going to be 3, which we don't care about, with a remainder of 15. Then n1 is going to get the value of 45, n2 is going to get the value of 15. Then what we do is we do the same thing again. So it's 45 divided by 15 is, what do we got here? That's 3 with a remainder of 0. So in this situation, we shuffle everything up again. So n1 is going to get the value of 15. n2 is going to get the value of 0. And then this is our end condition. So our algorithm says to stop doing what we're doing when n2 is 0. And then n1 is the greatest common divisor, which is 15 in this case. So really easy to follow method for getting the greatest common divisor. Now let's work on programming it, because that's the trick here. So I've got my scanner incorporated here so that you can test this out with different values, and we're going to see something interesting when this is done. So we're going to have our n1 and our n2. We'll have a remainder value, And let's prompt the user for the two values n1 and n2. So system.out.print enter value 1. And then n1 will get the value of input.nextInt. Now I'm going to copy and paste this to save a little bit of time. And it will say enter value 2. And then n2 will get that value. Okay, now on to the algorithm. So what we want to do is we're going to keep going while n2 does not equal 0. And why we do this as a while instead of a do while is this will actually protect us in the case that n2 starts at 0, because then you're going to get a division by 0, which will result in an infinite value. So you don't want to do that. So it actually prevents a value of 0 from entering the loop, which is just an added level of protection. Okay, so now what we're going to do is we are going to make our remainder get the value of n1 modulus n2. So step 1, we're going to divide and then find out what the remainder is. And then we're going to shuffle up all the numbers. So n1 gets the value of n2, and then n2 gets the value of the remainder. And that's it. That's the entire program. So this is what I was talking about before, that this just looks like magic to me, that this tiny thing finds the greatest common divisor. And if you told a lot of people, if they don't know Euclid's algorithm, they would look at this and not really understand what it's doing because it's so simple. So what we do is at the end, system.out.print ln, our greatest common divisor is whatever n1 happened to be at that time. Oh, whoops, add that on. Okay, so let's check this out. So we'll run this, and I'm going to put in what we had, 345 and 150. And we get our greatest common divisor of 15. Now, a frequently asked question here is, Euclid's algorithm says to take the larger value and divide it by the smaller value and get the remainder. So do we need to put an if statement here that will control which of these is in fact the larger one before the algorithm starts, pardon me. So let's just see what happens if we put the smaller value first, 150 and 345. And it finds it anyway. This is pretty cool. So check out what happens here if we reverse the numbers. So back to our example here, if I do this, n1 is 150, and then n2 is 345. So watch what happens when I start this. So the first thing that we do is 150 divided by 345 gives us, so this will be 0. You can find no groups of 345 out of 150 elements. So it's 0, but what's the remainder? The remainder is 150. Then what happens is we shuffle up all the numbers. So n1 gets the value of 345, and n2 gets the value of 150, and then it carries on as normal from right here. So essentially, if you get a smaller number divided by a larger number, all it has to do is run the loop one extra time, and then the numbers flip, and then it's ready to go. So all of this is just fantastic. And to think that this algorithm is hundreds of years old and predates computers is pretty incredible. So we can use this for a bunch of stuff. We might be using it in some future programs in order to solve some more complicated problems.